Assalamu alaikum. So today we'll discuss the second chapter, which is the modeling of the DC machine. So simply in this class, we learn how to model different types of the DC machine. After that, we learn how to control the DC machine. In general, we are interested in the torque speed characteristic of the machine. I will go, let's say, a fast review regarding the structure of the machine, the main components of the machine. After that, we'll discuss the state space representation and the transfer function of the DC machine. So as you know, in general, any machine consists of what? Of a stator and rotor. Huh? The stator is the stationary part, correct? The stationary part. And the rotor is what? Is the moving part, correct? Why we call it rotor? Because this type of machine is rotating. Huh? It is rotating. Now, sometimes we call it armature. Sometimes we call it armature. The rotating part, sometimes we call it armature. Why here we call it armature? Yeah? No. The induced voltage, the place where the induced voltage is induced is called armature. So if the stator was the place where the voltage is induced, then the stator will be called armature. Huh? But in general, for the DC machine, the induced voltage were in the rotor. That's why we call it what? The armature. So simply here, as we can see, the stator we can place the field winding on the stator to produce what? The main field, correct? The main field. And according to the right-hand rule, this is the direction of the field, correct? Yeah? So this is the direction of the field. Now, on the rotor, we have here conductors, and you know that the dot is what? Is out from the board, and the cross is what? According to the Robin Hood principle. Yeah? According to the Robin Hood principle. Yeah? So simply the same thing if we energize the rotor according to the right-hand rule, we are generating what? Flux. Correct? Now, do you see the relation between the field or the main field and the armature field? The angle in between is what? 9 degrees. Why? To produce the maximum torque. To produce what? The maximum torque. And how we can do that here? Although the rotor is rotating. Yes. But all the time, the angle in between is what? Is 90 degrees. Why? Because we have brushes. Yeah? Commutator and the brushes. And all the time, the axe will be pointing toward what? The brushes axe. So 90 degrees in between in order to produce what? The maximum torque. Now, in this scenario, who can predict the direction of rotation of the rotor? Is it clockwise or counterclockwise? Or I cannot judge. There's missing information. Yeah, according to the Fleming right-hand rule. This is the pointer finger will point to the direction of magnetic flux. The middle finger will point to the direction of what? Of the current. The thumb will be pointing to the direction of what? Of the force. So let's see. So this is what? The main flux. Let's see this one out. So this is the current. So here what I'm having? The force in this side. So simply this will rotate what? Counterclockwise. If this one will support it. If the other side against that, nothing will happen. So let's see here what will happen. The flux is never changing. The current is changing. Right? So the force
opposite side.
is the opposite side. So simply now the rotor is rotating where? Counterclockwise. Yeah. So according to what? According to the Fleming right-hand rules, we can predict the direction of rotation. So for this case, the rotor is rotating in the counterclockwise. Why am I having the bar? What? So you know that in general, I need to maintain the current to have the same direction under the same pole. Yeah? You see the first one here. Under the north, all the time the current must be what? Out. Under the south, all the time the current must be what? In. But you know that the rotor is rotating. Yeah? But I need to maintain the same direction of the current to maintain what? The same direction of rotation. If I change the direction, what will happen? Simply, the machine will never rotate. Yeah? Good. So how we can do that? Using the commutator and the brushes. So this is another simplified, let's say, picture of the DC machine. Consists of two poles, north and south, and a single conductor. Only a single conductor. And simply here what we have the commutator with the brushes. What's the function of the commutator and the brushes here? This is the first one, to provide a mechanism for rotation. If I have a solid connection, the rotor will never rotate. The second thing. Mechanical rectifier. Correct? It's actually, all the induced voltage are alternating. All the induced voltages are what? Alternating by nature. So simply this is what? This is a DC. Yeah? So the commutator with the brushes will act as what? A mechanical rectifier. A mechanical rectifier. So here, for example, let's see. If I'm energizing the armature with plus, minus. So simply, this will be the direction of the current, correct? Yeah? Who can predict the direction of rotation now? Now, you know that this is the direction of what? Of the flux, correct? Now, let's see. The direction of the flux. Yeah? Direction of the current. So, in the upward, correct? Yeah? The direction of what? Of the flux. The direction of the current. So, upward is the force, correct? So this is the direction of the force. Who can decide the direction for the second part? Now I check the first part. Huh? The same thing. The direction of the flux. The direction of the flux. Direction of the flux. Yep. Direction of the current. Flux. The flux. The current. The force down. Yeah. Down. Yep. So simply, this means that the machine will rotate in counterclockwise. Now, counterclockwise. If I need to change the direction of rotation, what I should do? So this is the first scenario. The second scenario. The ball. Correct. Here, of course, this is a parent magnet. It's a magnet. I cannot change it. But unless I'm changing the structure of the machine, in the design stage. But simply if the field was generated from a winding, simply I can what? I can reverse the plus and the minus across the winding, and of course I can change the direction of the flux, and this is sufficient to change what? The direction of rotation. Very simple. So simply now let's ask you a question. If I'm having a series connected DC machine, and someone changed the terminal, it will rotate in the opposite direction? Yes? Yes? Yes. Yes. Who say no? It's a series. If I change the terminal, I'm changing the direction of the field and the armature. Nothing will happen. Yes? Understood? It's a series connected. So in the series connected, if I'm changing the polarity, let's say, of the plus and the minus of the terminal, what will happen? The flux is changing and the direction of the current will change in the same time. So I'm maintaining what? The same direction of rotation, correct? Yep. Good. Here I'm having some pictures, let's say, regarding the stator. This is the rotor, and this is the commutator with the brushes. Now, this is the stator. Here I'm having yoke. In the yoke we have the windings, the field windings. Here we have the rotor, and this is the commutator with the brushes. And this is, let's see, a close picture of the brushes. And those are the main components of what? Of any DC machine. So simply this means that this machine is expensive, correct? Compared to what? If I'm saying expensive or compact with respect to what, correct?
Yes.
So let's say the benchmark, the reference for us is the induction machine, the plug and the play machine. Huh? So simply in the squirrel cage induction machine, I don't have any commutator, I don't have any slip rings. The wind rotor, I'm having slip rings. So I will never compare with that. So if I'm comparing with the horsepower of the industry, which is the induction machine, yeah? So simply I don't have commutator. Here I'm having commutator, correct? So this will be more expensive. It needs maintenance.
Yes.
Yeah? Why? Because those are brushes, carbon brushes, huh? While moving the rotor, the brushes will be eaten, correct? So with time I need what? I need to replace them. What else? All the time I'm doing short circuit, by the way. Why? While the commutator is traveling, two segments are shorted together. Yeah? So simply all the time you will see what spark. Correct? Yeah? But simply why this one we use it, it's simple. Before, let's say, the revolution of power electronics, before the theory of electromagnetic field, the revolution, electromagnetic field, the induction machine, the DC motor was the horsepower of the industry. Nowadays, no one uses it as a classical, let's say, DC machine. You can hear the term brushless DC machine. The brushless DC machine is not DC machine. It's a synchronous machine. But simply why we call it brushless DC machine? Because it has no brushes and its torque speed characteristic almost equivalent to what? To the separately excited DC machine. And under the vector control, we can control it as easy as the separately excited DC machine. But simply we need to understand the theory behind the DC machine and how to control the DC machine. Good. So some limitation, as we said, high maintenance because we have commutators and brushes. It's expensive, speed limitation, and there's sparking. Now, commonly used DC motor are the separately excited DC machine and the series DC machine.
Speed limitation
The torque speed characteristic of the machine is not that wide compared to the induction machine. Yeah? Yeah. And simply if I need high torque, I need huge machine. If I compare the torque per volume between the DC machine and the induction machine has higher torque per volume. What the meaning of torque per volume? Simply the same size of the machine, the induction machine can provide you higher torque. The meaning of torque per volume for the machine. So the most commonly used DC motors, separately excited, and the series, which mostly used for traction application. Now, according to the field or the excitation, we can classify the DC machine. So let's see the first one. Here I'm having two motors or two machines, let's say. The first one, the field is separated from the armature. So this one's called what? Separately excited DC machine. If the field and the armature are separated, this means that I can control the field alone, yeah, and I can control the armature alone.
Yes.
Yeah. Good. So simply this means that I can control the field current to control the flux, the main flux. and I can control the armature current to control the torque. So I'm having here independent control between the field and the torque. Yeah? So this one is what? Very attractive, very easy to control. Why? Because I'm having what? Independent characteristic between the field and the armature. Now what about the second one? The second one is what? Simply, what is the difference between the first one and the second one? The structure are the same, except that the field is connected to the same supply, let's say, yeah? To the same supply. Yes? So if I'm connecting the field to the same supply, this means that now I'm having coupling, yeah, between what? The field and the armature. If I change the terminal voltage, then the field voltage will change and the armature voltage will change, correct? Yes? So this one is what is more complicated to be controlled compared to the separate legs drive. Yeah? Now, if I need to plot the first machine torque speed characteristic, if this one is the torque, this one is the speed, it will be a nice linear, let's say, line, right? With certain slope. What about the second one? For the shunt connected DC machine, if I need to plot the torque speed characteristic. If this is the torque and this is the speed. Now someone will say, if I need to do that, I need to maintain what? I need to maintain the field constant, correct? And that's why here sometimes we are adding some kind of adjustable rheostat or resistance, correct? Because if I'm changing the voltage, I need to maintain, let's say, the field constant, yeah? So someone will say, if I'm neglecting the armature reaction, then the torque speed characteristic will be the same. What's the meaning of the armature reaction? Do you know this term, armature reaction? What's the meaning of the armature reaction?
بتضاعف الفلكس
Yeah. Simply, in the machine, you have two fluxes. One we call what? The field, the main flux. And the second one is caused by what? By the flowing, the current inside the armature, correct? Yes? Now, simply the armature reaction here, that the field or the armature flux will weaken the main flux.
On EB اللي كان
No, EB, this is the back EMF.
okay.
Now, sometime here, do you see those two squares? Those indication for what? The commutator and the brushes. The axe. So sometimes those, we can shift it. Either to the left or to the right according to certain angle to neglect
sparks.
the armature reaction. Yeah? Or sometimes we can introduce what? Interpole. Yeah? A small windings in order to neglect also what we call the armature reaction.
مش فاهم ايش الارمتشر رياكشن.
Now simply in the armature reaction, you have here two fluxes. Now, do you know the commutative and the differential operation of the machine? If I'm having two fluxes, if the two fluxes pointing toward the same direction, they are supporting each other. Yeah? If they are against each other, they are what? Resisting each other, correct? Now here, you have the main flux, which is coming from where? From the field. The field. Good. Then you have another flux, which is coming from where? From the armature. Now, sometimes the armature cause the main or generate a flux, some component of flux that weaken, behave against the main flux. So now the question: if I'm reducing the flux, the speed will increase or decrease?
If you are increasing the flux.
If I'm reducing the flux,
The main flux.
Increase.
yeah,
السبيد بيزيد.
speed will increase or will decrease. Now, simply if I recall this one, I must give it to you after discussing the state operation, but simply if I'm writing V, which equal RIA plus EA, which is K phi omega, I think.
Yeah.
And simply omega will equal to what? V over K phi minus IA over K phi. So if I'm reducing the flux, I'm increasing what?
Speed.
The speed. Yeah? So this is what we call the armature reaction. So without armature reaction, it's a nice straight line. It was straight line, supposed to be straight line. Yeah? This is without
Armature reaction.
armature reaction, yeah. Now with armature reaction, let's change the color with something else. And because while increasing the torque, this means that the current is increasing.
Yep.
Yeah? So this means that the reaction will be amplified or increased. So this means that the speed will increase. Yeah? This is what with armature reaction. Good?
So بصير خط كونستانت يعني؟ شو مبين؟
No.
زي
شو مبين
واحد
هذا؟
على اكس.
Simply, if you notice here, while the torque is small, this means that the current is small. So it will generate a small flux that will never interfere with what? With the main flux. While I'm increasing the torque, because you know that I can plot this one with what? With the I.
Yes.
Yeah? And this is what we call it the electromechanical characteristic. Yeah? The electromechanical characteristic. The current with the speed and the torque with the speed, we call it what? The torque speed characteristic. Or the mechanical characteristic. Now, while I'm increasing the current, which is the torque, simply I'm generating armature reactions, so slightly the speed will be higher. Okay. What else? The first one is the separately excited. The second one is what? Is the shunt. So simply, what about if the field and the armature in series? This is what you call what? This is what we call the series connected DC machine. Now here, in the series connected DC machine, the field current and the armature current are what? Are the same. So simply now, we have a conflict between the field and the torque. And the torque actually here will be proportional to what? I squared. So we have an linear characteristic, correct? Yeah? Now, this one has high starting torque, and in general, the no-load operation are forbidden. Why? Because in theory, if TL is equal to 0, then omega will equal to what?
Infinity.
To infinity. But you know that in theory I'm having friction. Or in theory I can say the friction equals 0, but in practice I cannot say that. There is a friction. Yeah? But even though this motor will rotate at a speed higher than the maximum speed, higher than the maximum speed that the shaft can handle. Yeah? And this is what a mechanical design parameter is, the omega max. So it's forbidden for the series machine to be operated or to run at no load. Yeah? Now what about if I need to merge between the, let's say, the benefit or the advantage of the torque speed characteristic of the shunt, or let's say the separately excited, or here the shunt and the series. In the shunt, if I'm neglecting the armature reaction, I'm having what? A linear torque speed characteristic, correct? I can operate at no load. Yeah?
Okay.
For the series, what I'm having? Huge starting torque. But it's forbidden to operate where? At no load. So what about if I combine? This is the idea from behind what? Combining the shunt and the field. So here I'm having what we call a short or long combine. And the same thing, we have what? Either the two fields are supporting each other, and this will be what? The cumulative compound. or they are operating against each other,
Differential.
and this we call what differential. Got it? Okay. Now, which one is recommended for the generator action? Which one is recommended for the motor action? The differential compound or the cumulative compound? Which one is recommended for the motor is cumulative and for the generator? Generator, yeah. Good. Why?
Differential generator, we need to reduce the generating torque.
We need to enhance the voltage regulation under the load. So, yeah? Yes?
Yeah.
So that's why we're using what? We can have a flat, flat, let's say, voltage profile for the generator. Now, simply here we have two combinations. The first one depends on where I'm connecting the series with the shunt. Is it long compound or short compound? Correct? Now, the second thing, the direction of the fluxes. If the two fluxes are supporting each other, this is what we call cumulative. If the series is acting against the shunt, this is what we call the differential. Why I say the series acting? Because the main flux is from the shunt field, not the series field. Right? This is the main. Yeah? So if the two fields are strengthening each other or pointing toward each other, yes, then this means that the total flux is the first flux plus the second flux. And this is what we call what? Cumulative. I'm accumulating the flux. Yeah. Now, if I'm accumulating the flux, simply, let's see. Now, what's the relation between the induced voltage and the speed and the flux? You know that the principle of the electrical machine is what? There's two principles of the electrical machine, correct? If I'm having a current crossing a magnetic field, I will generate what? Force.
Force.
This is the machine. The second one, if I'm having conductor crossing the field, I'm generating what? Voltage. The first thing, I'm inducing voltage. If I'm closing the loop, I will generate current. Yes? So the first thing that you will generate is what? Is the voltage, not the current. Yeah? I will induce the voltage. Then if I'm closing the circuit, yeah? If I'm, let's say, connecting the load, if I'm closing the circuit, let's say, in this case, a current will flow. Now let's see, which one is recommended for the generator action? Simply the differential. Why the differential? Now, do you remember the voltage profile of the DC generator? The voltage profile is what? The same as the torque speed characteristic, except that for the generator, I'm plotting the V output or V terminal with the current. Correct? Simply, while I'm increasing the current, I'm loading the machine. Correct? I'm loading the machine. So if I'm loading the machine, what I need? I need to rise up the voltage to compensate regarding what? Regarding the drop in the voltage. And how I can do that? If the flux is reduced, yeah, simply speed will be higher, so the voltage will be rising. Yes? So that's why it's recommended for the DC generator.
دكتور مش بالجنريتر السبيد كونستانت بتكون؟
Yes, it's according to the prime mover. But simply this one what will support the prime mover, the loading. Okay. The last one is what? The last one, imagine that the field is coming from magnet. You know the magnet? What we call it what? The permanent magnet. Simply in this case, I don't have any winding to generate what? The field. If I don't have any winding to generate the field, simply this means that the losses across the field circuit is negligible. Yes, because you know that if I'm having a current inside the conductor, it will generate a losses which equal to what? I square R. Yep. Now here I don't have any field winding. Why? Because the magnet is produced by what? By the bearing magnet. Good. So here only I'm having what? The rotor. Only the rotor. So the torque speed characteristic of this machine is identical to the split leg excited DC machine, except that I cannot control what? The field. Yes? So according to the efficiency, this one has higher efficiency. Why higher efficiency?
Less losses. No losses.
Less losses, not
No,
no
no,
losses.
in the field.
Less losses, because the field there's no circuit, actual circuit in the field, so the losses will be reduced, the efficiency will be higher compared to the classical, let's say, or the conventional separately excited. Yeah? Now, what is the disadvantage of this one?
Cannot control it.
We cannot control the field.
Yes.
Huh? We cannot control
The field.
the field. And you know that in general, I'm not increasing the field above the rating. What I will do, I will do what? Reducing the field. Reduction in the field. Huh? What we call it what? Do you know we call it what? We call it field weakening. Yeah? Weaken the field. If I'm weakening the field, I can rise the speed above the no load speed, the rated no load speed. Let's say, yeah? So this one, I cannot do it. So here, if I need to control, I will control below the rated speed alone. I cannot go above or higher speed. Why? Because I cannot touch the field. This is the first one. The second one. Do you remember the armature reaction? So with aging, there's a chance that the magnet will be weakened.
Yeah.
So simply after some time, we need to replace them. Of course, nowadays, the bearing magnet can handle until 20 years without any problem. But simply this is, let's say, a classical shortcoming of the parent magnet in this machine. Good. Okay. Until here, do you have any question regarding the type of the excitation, the structure? I think this is a short summary of what we already know in the machine. Huh? So now let's start with modeling of the separately excited machine. Now in modeling here, I can go with state space representation, which means that I will write the differential equation that describe what? The machine. After that, I can either go to Laplace transform, or instead of that, solving them using the state space representation, let's say technique or method we already know from the control system. Now here what I'm having, two circuits. The first one is the field, and the second one is the armature. So let's start with the armature circuit. So this one is what? The armature circuit. So now who can help me to write the voltage equation? You know that if I'm modeling a machine, I need to model the electrical part and I need to model what? The mechanical part, correct? And I need to find a coupling in between, correct? The electrical part alone cannot operate the machine. The mechanical part cannot represent the machine. The mechanical part alone cannot represent the machine. I need the electrical and the mechanical, and I need a link in between, correct? In order to represent, let's say, the mathematical model of the machine. So for the armature, let's assume that this is the rotor or the armature, and this one is connected to a load. And in general, the mechanical load is characterized by what? By inertia and viscous friction, correct? And let's assume here I'm rotating with certain speed, I'm driving certain load. Yeah? Now, who can help me with the mathematical representation for the armature circuit? For the armature.
VT
Yeah, VT
EA
equal
Okay.
plus IA RA plus LA DIA by DT. Yeah? Yeah? Simply here what I'm using KVL. Huh? KVL. Yes? And the knowledge of what? Of Ohm law and Faraday law of induction. Okay. Now, EA is what?
armature law.
The back enough, huh?
Vacuum.
EA is what? Is the back enough. Why I'm having back enough? If I'm having a field and there's a conductor crossing the field, I will induce EMF. Correct? This is the back EMF. Good? Good. So simply, the back EMF has a relation with what? With the speed. EA has
محتوى ال اللي هي شيء
the inductance.
او مش موجودة على الرسم
Let's put it here. Huh? It's actually here, but simply I can put it anywhere. In the end of the day, it's a circuit. Huh? So LA is the armature inductance. Now EA is proportional with what? With the flux and the speed. Yep. And because here I can fix the field, this is separately excited, so I can fix the field and maintain constant as the rated. So EA is proportional with omega. Yeah? So in general I can write EA will equal certain constant K. I think you like to have it be, huh? KB?
K.
KA? K, okay, I will fill you. KA multiplied by good? Okay. So simply now, someone will say VT will equal KA omega, yeah, plus IA RA plus LA DIA by DT. Correct? Yes? This is what for what? The electrical representation for the armature. Now what about the field? If I need to represent the field, it will be very simple. A series circuit, so I will say that it's VF will equal to IF RF plus LF DIF by DT. Okay? Good? Now, if I need to represent the mechanical system, it's J d omega by dt plus b omega must equal T minus T. Now, I need to find T. T is equal to what? The other side. Others? No other? Okay. Now, if I need to find TE, how I can find TE? TE, the electromagnetic torque, equal to what?
K I IA.
Now, let's see. I have another, let's say, magic for that. Imagine that here you are multiplying by what? By IA. What you will get? The first term is what? Pn. Yes. Is equal what? IA Ka omega plus what else? IA square RA plus what else? IA L A D I A by dt. Yeah? So the first one, which was VA IA, is the power input. This is what? Huh? The ohmic losses. The ohmic losses. Huh? So the losses. This is what?
Which
Huh? إيه؟
وجه الاندكتر ضرب تيار
إيه. This one. Store energy in the inductor. Correct? Yes? So this one has no relation with the mechanical power. Yes? So the only term that will be converted to the mechanical power is what? IA, K omega. Correct? So this one can be seen as what? Power developed. Yes? So from here I can say that the power developed, or the power that will be converted to the mechanical power, is nothing more than IA K A omega. Now T is what? We know that T is what? No. The power developed is what? TA multiplied by omega. So if I need to calculate TE, I will divide the power developed over what? Over omega. Correct? So if I do that, I will get what? This one is the power developed over omega, and this will be what? K. But here I think you use it KT, correct? IA. But you know that KT is equal to KA. Yes? If KA was described volt second per rad, I cannot say revolution per minute per rad, revolution per minute per volt. Huh? Simply KA must be represented in what? Volt second per rad. In this case, this constant is equal to KT, which is what? KT is what? Newton meter per ampere. Correct? Yeah? Good? So it will be the same. Huh? So simply this means that Ka is equal Kt in magnitude if and only if the unit of Ka is volt second per rad. Yeah? If it's volt per RPM, it will not be equal. In terms of magnitude, Kt is equal to Ka if and only if the unit of Ka is volt second per rad. And let me change this ugly curve.
كيف نقدر نحولها دكتور ولا تعطينا نصلح الناس الماشين زمان اخذت.
Simply, now what you have? In general, if I need to find the back EMF or the constant of the back EMF, this actually is the last slide. It's supposed to be the last slide. Let's discuss it here. One will say what I will do. I will operate the machine as a generator under no load. There's nothing connected to the machine. Then I will bring a prime mover with a constant speed. Then I will rotate it under constant field. So simply, according to that, I'm changing the speed, and now I'm having a relation between the speed and the induced EMF. The slope of that is what? K. Now here, you have the chance to measure the speed in RPM. In this case, the constant will be what? Volt per RPM. Or you are liking radian per second. In this case, the constant will be what? Volt second per rad. As a nature, they are the same. In order of magnitude, they are not. Simply, can you add meter to mil? Adding like this? No, you should uniform the unit. Now here are the same. If I need to use the same constant for the torque constant and the back EMF constant, then the back EMF constant must be written in a unit which is volt second per rad. Now if I need to make the changing, it's very simple. You will say that 1 RPM give me blah blah blah.
60 ثانية وبحول.
Yes.
اوكي thank you.
Good. So now what I'm having. So now I can write the mechanical part. Let's change the curve before that. So now the mechanical part can be written as J d omega by dt plus b omega, which equal kt ia minus t. Now, do you see this term? And this term?
The same.
No, not the same. One is the back EMF, the second one is the electromagnetic torque. They are the coupling terms. Yeah? They are the coupling terms. Yeah? Now, in the motor, I'm interested in this one. In the generator, I'm interested in this one. If I need to design a machine, if my target is to design a motor, I will try to maximize the torque.
Yes.
Correct? If I'm designing a generator, yes, my target will be what? Maximize the induced voltage. Yes? So this one is actually the interaction between the mechanical to the electrical, which is the induced voltage, and this one must be maximized or to be the key factor of the design if the machine is designed to be a generator. And this one is the coupling between the electrical to the mechanical, and this one must be maximized if I'm designing the machine to operate as what? As a motor. And I told you that in the drive, all the time I'm interested in the machine as what? As a motor. Good. So now let's see, I'm having the state space representation, or let's say the differential equation. Yes, I'm having. Let's rewrite it again. So the first one, or before that. Now, in order to write the mathematical model for the separately excited, I can carry with me the field. Or simply I will assume what I'm assuming that I'm giving a certain voltage here. Good? So the field is a steady state, reaching a steady state rated value. So now the field is constant, correct? Yes? And if this is the case, I only need to take with me the armature with the mechanical part. Assuming what? Yeah, and this is what we call the armature controlled separately excited DC machine, which means that I'm fixing the field, and you know that if I need to fix anything, I will fix it where? At the rated. At the rated value. The best condition for the machine is the rated value. Yes? So now here I'm assuming what? I'm fixing the field. I'm not controlling the field. And I need to write, let's say, the mathematical model to represent the armature controlled DC machine. So how I can do that? Very simple. I would say that VF is constant, which equal VF rated, and this will cause IF rated to flow, yeah, and this will cause the flux rate. Yes? So now what I'm discussing here, what we call the armature controlled DC machine. Voltage controlled DC machine. So only I need to write, let's say I will write VA, which equal to RA IA plus LA DIA by DT plus EA, which is we call KB omega. And for the mechanical system, this is the armature circuit. And for the mechanical system, we have the J d omega by dt plus b omega will equal kt ia minus ti, correct? So you know that the first thing, if I need to write the state space representation, I must put the higher derivative in one side and all the other terms were in the other side. Yes? Then I must make, let's say, the higher derivative constant to be equal to 1. To be equal to 1. To 1. So this is a very simple. So here I can say this is dia by dt will equal Ra over La, don't forget the minus. I'm rearranging the equation. Huh? Then minus Kb over La multiply by omega plus Va over La. Who can help me with the second equation? I will put the highest derivative in one side, which is d omega by dt. Then I'm rearranging the equation. So the first one, because here there IA here, I'm forgetting IA. So here what I'm having the first one, minus KT over J multiplied by IA, minus B over J multiplied by omega, and in the end of the day what I'm having, minus TL.
دكتور مش بوزيتيف كي تي.
Yeah, KT is plus 10. Yep. Good. So, you know that we prefer to write the equation in form of matrices. Yeah.
Yeah.
So x dot is equal to ax plus bu. So let's put it in matrix form. So I will say that d by dt, an operator, anything inside the operator will be differentiated. So this will be the IA, and here is omega, equal. So how I can read this one? D by dt of IA, d by dt of omega will be a 2 by 2 matrix multiplied by the vector, which is the IA, omega, plus another 2 by 2 multiplied by VA and TN. Good. Yeah. Now, who can help me with the first matrix here, the first element equal to what? Minus RA over LA. Huh? Simply go to this equation. Let's say equation number 1. Search where you can find IA, this one. Take its coefficient. Correct? And put it here. So this will be minus RA over LA. Now this one, the coefficient for
Omega.
yeah, the first equation, the coefficient of omega, which is
minus KB.
yeah, thank you. So this will be minus KB over L. Now here, can you see VA? Yeah, so what's the coefficient of VA? So 1 over LA. Can you see TL in the first equation?
No.
So what's the coefficient of that? 0. So who can help me with the second line? Go to the second equation. Let's assume this one is the second equation.
KT.
The first one is KT over J yeah, minus B over J, 0 here, and minus 1 over J. Correct? Yeah? Yes. So it's very simple. It's very simple. Now, according to our understanding of the state space representation, we know that this can be seen as x dot is equal a x plus b u. Yes? So simply this is what we call what? The state matrix. This is what we call what? The input matrix. And this actually what we call what? The state space. Yeah? State space. State variable. State variable. So this is the state variable, this is the state matrix. And this one is the input matrix. And this one is the input. Now someone will say, why you are adding TL to the input? Simply, VA is the input, correct? And TL is what? TL is what? TL is input. But I cannot control it. So I will not say it's input, I will say disturbance.
Okay.
Yeah? VA, I can control it. So this is the actual input. TL is input, but I cannot control it. Correct? Yes? By the way, never and ever control TL in order to control the speed. This will be useless. This will be as well. as while you are driving, you are throwing the people from your car in order to regulate the speed of the car. Yeah? So TL is what? Your problem. You should live with. You should solve. Yep. So simply here, TL is input, but this input I cannot control. So instead of using the TM input for that, I will say it's what? It's a disturbance. And wanted input. Correct? Yep. So if I need to study the stability of the system, you know that the stability of the state space representation is actually connected to the eigenvalue of the state matrix. And how to find the eigenvalue? You say it's very simple. The determinant of lambda I minus A. Correct? Yes. According from where? 2004, correct? Linear algebra. Yeah, you say it's out. We'll call Dr. Saleh. Dr. Dihan. Before Dr. Saleh. So let's say. So simply the eigenvalue of the stability here of the system is connected to the eigenvalue problem. Of the state matrix. Good. So which actually the determinant of lambda I minus A equal to 0, and this is what we call it, let's say psi lambda. What we call it in the control, the characteristic equation. Now this characteristic equation is 2 by 2. Yeah, مثنى. It's 2 by 2. Can you calculate the characteristic equation here? It's 2 by 2. So we'll say the first thing I will do is lambda I minus A. So here will be lambda plus this one. Lambda plus this one. I will toggle the sign here because I'm having minus. Then I will multiply the diagonal and subtract from the multiplication of the diagonal. Right?
Determined.
Yeah, the determinant. It's actually the determinant. Huh? It's the determinant. Yeah? So we can do that. So let's assume I did that and I'm having the final, let's say, answer, huh? Which is, so psi lambda, the characteristic equation, is equal S squared plus RA over LA plus B over J multiplied by the S, and I'm having constant term which is called RAB over J plus KB squared over JLA equal to 0, and here I'm having LA. Yep. Now this one is stable, unstable, or I cannot judge. Or I need to do some other verification. Should I? Listen. Hamza. Second order system. Can you judge about the stability? Or simply you need to check something
شو
else?
طول البولس هاي هو شوف
ممكن نقول ان استابيليتي بلس
ما شاء الله تبارك الله.
ما سمعت.
Now, your answer is correct, but simply here you need to find the exact location. Hamza? مثلا say wait. RA is positive, LA is positive, B is positive, J is positive. Yes. So simply according to Ralph, the second order system, the necessary and sufficient condition for stability is that all the coefficients must have the same sign.
ممكن ناخذ من كون من اولها انه كونها بوزيتيف انه اقدر اقول
Yeah. But this one is only for what? For second and first, by the way. But first, no one say Ralph because the first is already we have the exact root. But for the second, I need to do the math. I need to calculate the exact location and solve it. Although I'm having a close form for that, but simply someone say, wait, why you should do that? Simply positive, stable. this one was negative, this must be negative, negative. All the coefficients must have what? The same sign, and this only for what? For the second order system. From where? From EE440, which is the control system from the RAF. Chapter 6. Good. So this means that if you are plugging the DC machine, it will rotate. You don't have a problem. If this one was unstable, if you are plugging the DC machine, it will what? It will over accelerate, or it will never rotate. Correct? So simply this means that the split legs DC machine is self-starting, stable, plug and play. Yeah? Good? Good. Now, someone will say, in the classical control system, we used to deal with the Laplace transform. Yeah? Why is that? Now, this one's what? This one, ordinary differential. Yeah? Why we call it ordinary differential equation? The constants, the coefficients are constant. And simply linear. So that's why we call it what? Ordinary differential equation. Although this one is simple to be solved, but solving algebraical equation is more straightforward. Yes?
Yes.
Yeah? Imagine you have what? Instead of x dot ax plus bu, you have what? X is equal ay plus u, for example. So can you solve for y? Yes, I can do that. Yeah? So in general, solving algebraical equation is more straightforward and more easy than solving what? Differential equation. And this is the idea behind what? Laplace. So we can have Laplace transform. Let's see. As this best model, so I don't do this one because already I did that. Oh, good. Come back. Yeah. So let's block diagram and transfer function. Today I think I can control it. Smooth. Yeah, that's good. So for the block diagram, this is also another technique, which means that I can represent the system using state space representation, the first one, or I can use Laplace transform in order to simplify the thing for us, in order to deal with what? With algebraical equation. Huh? Now, let's start with the armature equation. And automatically I will try to plot the block diagram. So now if we recall, VA is equal to what? RA IA plus LA DIA by DT plus EA it was. And we know that EA is nothing more than KA equal, KA multiplied. Now let's try to take Laplace transform for this one under the assumption that the initial condition is equal to what? To 0. Good. So you know that if I'm having any time function, if I'm taking Laplace for that, I will write it as what? Capital letter, correct? Yes? So VA of t, instead of that, if I'm taking Laplace for that, it will be what? VA of s. IA of t, it will be what? IA capital of s. I capital. Okay. So let's try to do that. So let's take Laplace transform here. If I'm taking to the first side, I will take it to the second side. So this will be VA of s will equal. This will be RA, the constant, IA of s plus LA for the differentiation of both what s. IA of s, I'm neglecting the initial condition. I'm assuming the initial condition equal to what?
0.
And here plus EA of s. Now, I need to solve this equation with respect to IA. Is it difficult?
No.
Who can give me the equation with respect to IA equal to what? So simply you say that IA is equal VA minus EA over what? LAS plus RA, correct? So simply this one, the block diagram is what? You know that if you need to represent any linear equation, you need multiplication and addition, correct? By multiplication, I'm adding the division. And by addition, I'm adding what? Subtraction.
Subtraction.
You need only two operators actually. So let's see this one. So here, this means that, let's put it here. Huh? So this is the VA. I will subtract from it what? Minus EA. Then I will multiply the result by what? 1 over LAS plus R. The output is what? I. That now, do you remember TE was equal to what? Yeah, multiply by
Omega.
IA. So in term of Laplace, it will be TE in term of Laplace, KTIA of us. Correct? So if I multiply this one by the constant of the torque, or the torque constant, I will get what? T. Yes. Yes, I know. So now, I like control. So let's write down the mechanical equation. J d omega by dt plus b omega is equal TE, which is TE, let's say, minus TI. Now, in terms of Laplace, this will be what? J S plus B all multiplied by omega of S will equal to what? T minus Ti, correct? Now, if I need to solve with respect to omega of S, this will equal to what? Te minus Ti over Js plus B, correct? So now here I will add a summing point, and this will be Tl minus. Now, if I multiply by 1 over Js plus B, what I'm getting? Omega. Now, do you remember the backing off equal to what? So now, if I'm multiplying this one by Ka, what I'm getting? And this is the block diagram of what? Of the voltage control. Yeah, DC machine. Good? Good. Now this one. Open loop or closed loop?
Close loop.
Open loop.
Open loop. Huh? Now just a minute. Now let's change the color. West. Let's change the color. Let's change the color with the red. And let's try to put a dash box which represents the machine itself. Yes? Correct? It's supposed to be a box. It's not a box, but it's supposed to be a box. Yeah? Now, what inside the box is the physical system. So this is the plant. Yeah? Now, in terms of control, this is open loop. Why? Because I'm not changing the input.
بس مش لما نزيد السبيد بتزيد KA بيقلل.
What the definition? Okay. What the definition of the closed loop control system?
Output depends output depends on the input. Or input depends on the output.
You can sense the output so that you can change the input.
The input is changing according to the knowledge of the output. Yes? Here, there's a reaction. It's a physical thing. You not control it.
okay.
Yeah? Now here, with the meaning, imagine that you have a DC machine. I'm imposing 10 volt. It will rotate at certain speed. Yes? Let's assume you did the math and say that 10 volt will give me 10 rad per second, roughly speaking. Then you are imposing the 10. It will rotate at 10 radian per second. It can be plus minus, it can reach 8. Yeah? If you're changing the load, the speed will drop. It will never maintain the 10. Why? Because the output is already calculated based on time. Yes? So in terms of control, this actually is open loop. Why? Because simply the input is not changing according to the knowledge of the output. if I need a closed loop control system, I must measure the output. Then I must calculate the input according to the output. Yes? Good. How many inputs here am I having? Two. Anything inside the block diagram is input, anything out from the block diagram is output. So this one has two inputs, one output. Simply this one we call it what? Disturbance. Why? Because we cannot control unwanted input. Now, you know that I need to calculate in the end of the day omega of t. Yeah? Omega of t. How I can do that?
Laplace inverse.
Yeah, Laplace inverse of what? أي معنى؟
Omega S.
This one?
Oh.
No.
بنطلع اوميجا اس على دي.
He's a genius, by the way. Do you know why? He is a genius. He said that, wait. Imagine that I'm using high gain in controlling the current. If I'm using high gain in controlling the current, then here I'm having what? K multiplied by the current, correct? Then you know that I can reshape the block diagram. If I need to put K here, I will divide by K, correct?
Yes.
So KT over the huge K is what? So this one will be what? 0. Huh? And simply this means that now the current inside the machine is equal my reference. Correct? So at the end of the day I will be what here? Torque reference subtracted from the actual torque multiplied by first order system. And this valid simplification, by the way. Yeah?
No.
Yeah, this is a valid simplification. Yeah? سليمان. Yeah, سليمان كده. شو كان السؤال؟
اوميجا اوف تي.
Yeah. But simply here, because we have a time and we have block diagram. So simply I need to find two transfer functions. The first one as seen between VA and omega, and the second one Ti and omega. Then omega of S will be what? The first G1 multiplied by its input. The second transfer function multiplied by its input, which is the superposition. Yeah? The superposition. So, for that here, we need to find two transfer functions with G1, the first one, where the output is omega and the input is VA. And we need to find the second transfer function, G2, which is omega with respect to L. Of course, I need to do the superposition, which means that here I will kill TL. And here I will kill what? VA. Then omega of S will equal G1 multiplied by VA plus G2 multiplied by TL. And omega of T will be nothing more than Laplace inverse of omega of S. Good? Yes? The high gain later on I will discuss. How I can reduce this one to a first order system. Now, what else I need? Until here, this okay, but simply I need what? I need the knowledge of RA. I need the knowledge of KA. Yes? I need the knowledge of KA, KT, otherwise I cannot control it in the end of the day. Yes? So how I can calculate, let's say, the electrical part, which is the RA and LA. How can I do that?
مرتين دكتور.
How I can, now, this model without the knowledge of the parameters is useless.
Oh, okay.
Yes? So I need the knowledge of the parameter. Someone will say you can find them on the nameplate. Yes? I will say yes, but imagine that after a certain time there's aging, or simply the nameplate was removed, or simply you have a DC machine without a nameplate.
مش في tests الأول.
Yes, so simply I need to do some tests in order to find what? The R, LA, RA, and KT, and KA. So the first one is what? How to find RA.
Test والshort circuit.
Open circuit and short circuit. Okay? Simply, I will deal with that with much simpler thing. Huh? Imagine that you are doing the first thing, the block rotor. If I'm doing the block rotor, simply I'm having what? A first order system where the input is a voltage and the output is what? Is what?
Torque.
Come. Yeah, of course. But KT, I don't know. I know. Huh? Yeah? Imagine that I'm doing a block rotor, which means that I'm imposing a small DC, otherwise my hand will be out. Huh? Small DC. Step Then I'm capturing the current response. What information I can get?
Time
So
constant.
so the first thing what I will do, I will measure RA and LA in the same test. To do so, I will do block rotor. What the meaning of block rotor?
يعني بلف
أحمد إيش block rotor?
cannot rotate.
So simply omega equal to what?
Omega equal to 0.
To 0. So simply I will end up with a very simple first order system. The input is VA and the output is what? Is IA. And this one is 1 over LAS plus RA. Now, let's do a step voltage. So this is a VA step. In terms of Laplace, it will be A over S, correct? Then I will record the current waveform. It will be what? First order system, it will never peak. So it will be something like this. Yes? So this one is what I steady state. So from I steady state, what I can calculate? RA. Yeah. Yes? So simply I will say that RA is equal to what? VA over I steady state only. But simply this one already has the brushes resistance. Correct? Yeah? But simply in the end of the day, I need the equivalent armature resistance. Good. Now, how I can calculate the LA? The tau.
Tau.
So simply we know that, what's the definition of the tau? Huh?
0.63 of the
It's 1 minus exponential minus 1 of I steady state, which equals what?
0.67.
0.632 or 23?
0.67.
No, 0.632 or 23, that's it. Of course, that's why I all the time say 1 minus exponential minus 1. It actually 0.632. So this would be 0.632 I steady state. Then I will project it in the time axis. And this will be what? Tau. Now the time constant for RL circuit is equal to what? L over R. So this will be LA over RA. So now I can calculate LA, which equal to what? Tau multiplied by yes. Yeah.
I get RA and then
Yes. I'm getting what? I'm getting RA and LA. Very stressful. Now, can I measure the inductance, the armature inductance, using another technique? Of course, someone will say I can use the DC test. You know the DC test? I will impose a DC to the armature under no load. Huh? You know the inductance is what? It's short circuit in the DC system. Yeah, in the DC analysis. Then I will say that V over I is equal to what? To the R. Yes, I can do that. Now, I can also calculate the inductance using AC signal. I will inject a small AC signal, of course, all the time under block rotor. Then I will calculate the current. Yeah? V over I is equal to what now? Z. And Z is equal to what? The square root of R squared plus omega squared. Correct? So I can resolve it and I will find what? The LA. But this one is most straightforward and nice. Yeah? Good. Now, how I can find the constant, the back EMF constant? This one was there. The inductance one there. The back EMF constant. I have mismatch in the estimation. So I'm putting more slides than I need. Whatever. So now the back EMF, how I can measure the back EMF constant?
وانا عامل لوك للروتر بدرس التورك
No, no.
بس
The no load test. But as a generator. Now here I will drive the machine as a generator.
Okay.
Yeah? Which means that I will bring a prime mover. Now this is my machine. My machine now is driven using prime mover. Let's say another motor. Then here I will measure the terminal voltage V open circuit, let's say. And I will record V open circuit with respect to omega. It will be some kind of straight line. The slope of that is what? Is Ka. Now, if I'm having K, I'm having what? Kt if I'm describing Ka in what? In volts second per round. Correct? Yes? Good. Now, how I can calculate or measure the inertia and the viscous friction? How I can do that? Think about it.
Repeat the question.
How I can measure the inertia and the viscous friction coefficient.
After driving the machine by the prime mover شوف قد ايه بدها قبل ما توقف.
No. Now see here, I need another test because now I'm having another machine connected to the rotor, so this will change my inertia. Yeah? So now, no, I'm discussing that I need another test in order to measure the inertia and the viscous friction. Now, do you remember Sliman? Do you remember Sliman? And recall that if I'm using precise current control, which means the meaning of the precise current control or BI current control, in the end of the day, I'm using BI current control. Why we will use BI current control? Because the integrator will rise the type number by 1. And simply the DC machine, the relation between the speed and the voltage is what? Is type 0. Yeah? So if I'm adding integrator in the loop, I will rise the type number by 1. So this means that what? The state error is equal to what? 0. If the system is what? Stable, of course. If the system is stable, then the steady state error will equal to 0. So can I rely on that, which means that the current control is much faster than, let's say, the mechanical part. So this means that the current inside the machine is my reference. Yeah. So now what I will do, I will give step reference for the current, and I will calculate the speed response. Yeah. Yeah. The speed response now with respect to the torque as input is first order. Correct? What I will get, omega steady state, yeah, and time constant. Correct? And from omega steady state I will calculate what?
تورك لود بالنص ايش بعمله؟ بحطه يعني لوكت ومره بين الكرنت والاوميجا في تورك.
TL 0.
زيرو.
So simply in the end of the day, what you will get? You will get like free run machine, correct? No load machine, no load tested. Yeah. So if I'm giving now a low current reference, a step, I will get what? Step or response, let's say in the speed, which has omega steady state, and I can calculate the final value, or let's say the steady state speed and the time constant. And from there I can calculate what? The B and the J. Yep.
بس شو المعادلات اللي صار من بي وجي؟ مش عارف ايش فاهم.
Now, if you agree with me that I can reach this one, this is the IA reference as input to the 1/J S plus B, and here is omega, and TL is equal to 0. Now this one, if I'm giving a reference current, a step, I reference, the speed response will equal to what? Time and omega. First order system, you will never peak, it will have something like this. Yeah? So this one is omega steady state, correct? Omega steady state from here I can calculate B.
اوكي بس قبل شوي استعملنا تاو عشان نلاقي
Yeah, just a minute.
مثلا.
So from here I can calculate B, yes?
آه.
Then I will go 1 minus exponential minus 1 of omega steady state. Then I will project it here and I will find tau mechanical. Now tau mechanical is equal to what? J over B. Ah, by the way, you don't know how to find the time constant?
ما هو هذا سؤالي.
Yeah. Now simply for a first order system, the general form is a DC gain, K DC over tau S plus 1. So if I need to calculate the time constant, this means that this must be 1 coefficient. So in order to find constant here, what time constant, what I need to divide by what? By B. So I will have 1 over B over J over B S plus 1. Compare now. The time constant is equal to what? Two rational functions are identical if and only if n is equal to n and d equal to d. So now, can you give me KDC equal to what?
1 over B.
And tau equal to what?
J over J.
Yes, the same thing was for the electrical part. It was 1 over LAS plus RA. I need to write it in standard form, so I need to divide by what? Yeah, so 1 over RA, LA over RA, S plus 1. So this is the DC gain and this is the time constant for the electrical part. Good. يعطيكم العافية.